Okay, so again, welcome to the JI today. Rick and I really want to take the next 15 minutes to go through 2 steps of the design process, from CT MRI to a surface model via segmentation, and then cleaning that model up in order to then print it and put a flow pump through it. So we're so happy to be a Stratasys 3D Printing Center of Excellence in Healthcare. It just makes sense. The JI has domain expertise in devices with all the medical device manufacturers that come through, the physician expertise downstairs with the imaging systems and the partnerships we've made. Stratasys obviously has a huge history in 3D printers and PolyJet resin materials, and together we hope that we can accelerate the pathway to using 3D printing for healthcare applications. So in the past 3 years, we've started in the neurovascular space. So here you can see one of the first models that we ever printed. This shows the intracranial anatomy. You can see 2 carotids on either side of your neck, and then a basilar artery which comes up through your spine in the back. And then they branch out into a whole bunch of vessels in your brain down to your capillary bed, but we segment down the anatomy to usually around 1 millimeter, and then we can post-process and clean. So we started in neurovascular with Dr. Siddiqui, Dr. Levy, Dr. Snyder. And then when Rick was an intern, we moved out into structural heart. So this model right here is the one that I'm holding in front of me, so I'll pass it around. A physician, Dr. Iyer, came to us with this case. It was an elderly lady who had mitral valve stenosis and severe regurgitation. So they wanted to try using an endovascular mitral repair technique. So inside this model, feel free to open this up as you go around. You can see that calcified stenosed region. It's black because we coated it with a radiopaque material. And then the physician was able to put this model under fluoroscopy. We hooked it up to a flow pump, and this is the one Pam was talking about earlier. He decided to use a different size valve and take some precautions in the procedure. Since then, we've done a couple more in the heart space, and our most recent addition has been abdominal aortic repair. So this is what I've been working on with some of our doctors, Dr. Drisky, Dr. Curl, Dr. Harris. This is a very complex case in which you have to control many wires and catheters all at the same time from multiple access points. When you deploy these grafts inside a whole new pipe you're laying, there's little holes in that graft that line up with your SMA artery to your gut and then the renals to your kidneys, and it's super important to keep those open. So we were able to print these out for physicians to practice those techniques before they use this graft for the first time in a patient. It proved invaluable, the amount of time we spent on these models, and I had the pleasure of going into the OR to kind of quantify the experience. So I'm going to pass it over to Rick to talk through the beginning of the design, and then we'll go out to demo.
Awesome. Thank you, Karen. So the model design process is essentially 4 steps. We start with a patient scan. And this could be a CT MR, any volumetric image. You can even do 3D ultrasound, though we're working on that still. After you've got a scan, you go through a process called segmentation, which, to put it briefly, is just to pull out all of the structures that you're actually interested in. If you're interested in the heart, you pull out the chambers of the heart, the valves, the same thing, bones, whatever you want to actually fabricate. But unfortunately, because we are limited by the resolution of the scanners, there needs to be a cleanup process. And it's not good enough to just smooth, apply blank filter, and throw onto the next step. We really do actually need to spend some time with it and build the model for the purpose that it's going to serve. That's the functional design aspect of this is really key. And then after that, we send it to the Stratasys 3D printer, and there's no other technology like PolyJet that can fabricate this soft, compliant material along with the digital blends. They're the best. End of story. Just some notes about this stuff. Patient scan files, DICOMs, CT or MR, highest quality you can get. Absolutely essential. For segmentation, put up a couple different softwares here. Toshiba Vitria, Simpleware Scan IP, and Mimics are the 3 big paid ones. There's a couple free ones that you could search for as well. Cleanup. There's a whole lot of options out there. These are free. The ones that we've got up. Actually, Magix is paid, excuse me. But Magix, Mesh Lab, Fusion 360, and Mesh Mixer. We're going to be demoing Toshiba Vitria and Mesh Mixer today for you. We're going to walk through an example of the heart actually building that model that was being passed around right now. So to refresh everybody what a CT scan looks like, as we slice down side view, we see the axial slices along the yellow line. As that slices through the heart, you've got contrast in the chambers and in the arteries. And this allows us to see the lumen, the space filled up by the cardiac chambers. And this is what we're actually going to be pulling out of the images. For segmentation, I'm going to run through a couple manual methods. If you were so inclined, you could sit here and choose points on an individual vessel. So you've got the aorta up there. It's highlighted in the red crosshairs. If you picked a point there and then applied a mathematical formula and went up to the other side and picked a point on the descending aorta, you could actually propagate a front along that lumen where the contrast is high there and pull out a surface model just like that. Now that's far from perfect, but it saves a lot of work rather than having to manually do that yourself. This is a manual method though. Another really simple one, thresholding. Anything above an intensity value of 300, pull out. That'll give you, some bones, some contrast, whatever. This was probably 600 or 700. And this is actually the calcified mitral apparatus. All of the calcium that had built up on this patient's mitral valve is shown there. It's like it turned into a bone, and that's what it was viewed on the CT like. So that was actually extracted just in this thresholding step like that. So I think I'm going to demo Vitria right now. So let's see if I can get this to work. Table laptop. Okay, so we start with the cardiac analysis screen here. And this is the generic view that pops up as soon as you open it. I'm just going to bring this out. We can sort of slice through, and this is sort of the same heart that we looked at right before. And it does all sorts of nice centerline tracking, but I could go on about this for a while, but we'll keep it short. This is the interesting part. What Toshiba's doing is building a machine learning library of the segmentation tool, of the segmented anatomy, and they're incorporating this to do automatic vessel recognition. So if we rotate around, you can see an outline of the heart, just rendered volumetrically from the CT image. If we hide this, this section that it's displayed as heart, we can see vessels. And we've got the ascending aorta and a bunch of the main coronary arteries. We're looking, the red highlighted one is the LAD, the right coronary, and the circumflex. And it also picks up a bunch of the side branches along it. But we want to go to the absolute limits, so this is not good enough for us. So what the software allows us to do, I've got the right coronary artery highlighted there. You see this vessel here isn't actually selected by anything. For whatever reason, it couldn't pick it up. So I'm just going to grow this vessel, add 2 vessels, and now when I hide the heart, there it is. So we can repeat. And working off of a projector. So we can repeat. We'll do one more maybe. Let's choose this one here. There we go. And I want to grab that vessel right there. And I'm actually going to do it a little bit too long, so we can give Karen a hard time in the next step. Give her something to show you. But add 2 vessels. We can see that I held on just a little bit too long. It grabbed some noise there, right? That's probably some muscle, or it might be a feeder, but it's really noisy. So I'm going to say this is okay. We'll make it in and delete all that in the next step. With Vital, I can export as STL, and it gives me a little bit of a preview window there. And this is a pretty good computer. It's important to have a good workstation when you're doing this. Regular hospital computers will not run this. It won't happen. So spend, the money, it's worth it. Create STL, and it's going to do its thing. And I am going to go back to the study list now. And in the results section, we have this STL. And I'm going to save it right on the desktop as test me. And I'm not going to open it up yet because Karen's next.
I hope you made it hard.
I hope so too. Let's see.
Okay, so Rick has segmented for us, and now we need to clean it up. So Rick mentioned that we're going to use Autodesk Mesh Mixer. This is a freeware that you can get online. It's really, you would think that a SolidWorks or a Pro-E, some kind of CAD program would be best for this, but the anatomy that we're working with is not, it's not geometric shapes. So Mesh Mixer is really good with its algorithms of working with non-geometric shapes. And our goal is to make a continuous vessel. So you can see the difference in that heart, the resolution from the segmentation to cleanup step. So here you can see Rick had picked out all the big structures of the heart. And here's the original and the cleanup. So you can see he smoothed out some of the vessels, he created some more inlets and outlets, and that's exactly what we're going to do. So here's his solid structures. So if that model is still passing around, you should be able to see that mitral calcification. And we kept the spine in so that in the step of Mesh Mixer, where we add in a solid base, you know the anatomical position, so that when you use these under X-ray, it will be the same thing as a patient laying supine on the procedure table. So this is the mitral valve calcification to begin, and then revised. So this is a nice video. You can see around. He had taken the pulmonary arteries and veins and condensed them down into a couple inlets and outlets rather than having so many tubes that we have to control fluid with. And then you can add on a base for the anatomical position. Here you can see through the pink space of the cardiac structure, and you can see that, is it a video?
Yep.
My bad. Wait. There it goes. And now you can see through that mitral valve up to the ventricle and out towards the aorta. And you can see how stenosed that is. So a physician has to figure out how to place a stent graft in there appropriately. And then we send it to a printer. So at this stage, I'm going to transfer us over.
I have a question before printing.
Sure.
So how do you quality control that model before it goes to printing? So you did the segmentation.
Mm-hmm.
I'm assuming there's some sort of overlay so that you can see that your segmentation is accurate.
Yeah.
So do you know with a specific, each different type of software, is it going to change the lumen, or does it add to the wall? Like, so you'll know the specifications of what you're doing?
Yeah, that's a really good question. That's something when you do 3D printing, it's super important that we start validating a lot of this. There's some softwares out there that you can compare point by point and see what your differential is between what you segmented versus what you printed, or what you segmented versus the original anatomy. It really comes down to how much time you spend on your segmentation. I can spend a complete day segmenting something to make it absolutely perfect, but at what point is that minuscule sub-millimeter quality necessary?
So how do you perform your quality control?
So right now we've been using Cloud Compare to compare points in space. A lot of the paid segmentation softwares can do some visual analysis for you in some of their back-end programs, but that's something else we're looking into. I don't know.
Do you ever reload your STL file and compare it to the axial? I know in Mimics you can do that.
Yeah, that's what I'm talking about. Mimics does that. You can load back your STL and see it in parallel with your CT scan. Okay. We have methods that we can do that with more coding and software stuff using Cloud Compare, but Mimics does a good job of doing that.
Cloud Compare similar?
No. It's actually not. It was never intended for the purpose we're using it, but
yeah.
It registers assigned distance transform between two-point clouds.
On high resolution mode, the comparison between the surfaces, it is better than the resolution of the imaging detectors. So when you compare them, it is under 250 microns, and that I wouldn't believe it since you start with a 500 micron resolution imaging system. And the comparison, it is taking each point and do a root mean square difference between the points of the two surfaces, and then you paint it in 3D as a intensity plot. So you kind of like see if somehow the residual material stays in, you see differences of maybe 1 millimeter. But if it is perfectly clean, then you see below the inherent resolution of the imaging detectors or the method.
Okay. For the sake of time, I'm going to go through Mesh Mixer, and then we'll have all the time that's left before 11 for any questions that you guys have on any stage of the process. So this is what Rick just segmented, those coronary arteries. You can see it picked up these main vessels really, really well at the right coronary artery, but it didn't get all the small branches. So Rick could have spent much more time on that segmentation and getting those small branches. But remember, he said he was going to make it difficult for me. And he region growed a little bit too long on this vessel, and you can see that that's the muscle tissue and maybe some feeding branches that he picked up as well, so we're going to have to clean that up.
That is a typical heart motion artifact that you get. And it depends. You can use, depending on how you select your scanner to do your reconstruction on an R2R, an SPQR wave. So in this case, we go at 70% when the heart is at most at the rest. But obviously, if you have a patient with arrhythmia, then you're running into problems.
Each anatomy that you're trying to pick out has its own nuances of when the image is taken, right? So Mesh Mixer interface is pretty easy to use. On the left-hand side, you have all the different things you can do. So the sculpt tools, you can see all the different options that you have. What it allows you to do is on a surface, smooth out a little bit. So if I zoom in, I can smooth the surface, something that's more easy to see. If I inflate, you can see how I can bulge it out. I can shrink it back down to what I wanted. But you can see how this could be helpful on like some of those artifacts. You can even do something where you pick a surface and you drag it outwards. And it's really easy to just Control-Z, undo what you did. Let's see. So now what I want to do is, in order to make this a 3D printed model that has a flow lumen, you need a continuous structure. There can't be any discontinuities, there can't be holes. It has to be a solid structure that's encased. So what I want to do is go down through the vessels and make sure that there's no holes and it looks good. So this side looks really awesome. You can see this bifurcation. It splits in two, and then it ends when the segmentation couldn't continue. So if I look at this artifact over on this vessel, some things I might want to do to it, I can use some of those smoothing tools. So I really like Bubble Smooth. I can select this vessel. Let's make it a little stronger. That's not doing what I want. So I can even try inflating and trying to get that back to what size I think it is, and then compare it to the CT. So you can see it's too stenosis there. So maybe I'll build that up, and you know what, I made that LED, it inflated too much, so I can decrease my size and focus right on just this branch. So you can see that comparison. Down towards some of this mess over here, this definitely looks like artifact. So I can select just this portion, and then I can delete it and fill it in. So that looks more like it was to the natural contour. And then once I accept that, I can go back into my sculpt tools. And where did it go?
Does that interface with haptics?
Excuse me?
Does it interface with the haptics device? To get
Yeah,
closer
when the
feedback?
light comes down.
I think it may. Does it?
No,
I don't know.
they're having issues working with the stereo
Do they
views.
use
And
freeform? So it's basically like that with the force feedback haptics you would virtually carve?
it would be wild. I would love to see that.
That's
what you guys
our
use?
models of, yeah.
Oh, cool.
I
Which,
think that would be something definitely I would want to try.
It's
Couldn't-
nice to be able to touch it. and
Couldn't
see.
you use Wacom stylus devices?
You don't use that
You could.
device? It's almost-
Yeah.
you just
Not right
take
now.
it
We
off.
just use fancy messes.
It's nice.
This is one of my favorite parts of my job because it's almost like you're a sculptor at
Yeah.
the same time.
One of the issues that I encountered when working on something like this was that I was concerned with the amount of subjectivity that I was inputting into the system. It seems to me as this is an artistic process more than a scientific process. What kind of validation or what kind of guarantee do we have that the subjectivity of this is not going to affect the anatomy at the time of the print?
Sure, and that's what we were talking about before with the taking your STL and pulling it back into your CT slice view to see how well you did, and then using some mathematical techniques to calculate if you're this far off on this distance of the vessel to the actual vessel versus your model, calculating how well you did. That's something that's big in the research world right now, and I defer to Chip on this one because my master's thesis has not gotten to that point yet. And we can talk
Definitely
more when we're...
the heart. It is by far the most complicated to get, and the farther you go into the distal and you go towards the apex to the heart, the harder will be the vessels to model. So that is for us like a sort of a holy grail, how to model these vessels, because we're looking into understanding how the flow affects distal feeding of the tissue and how we handle these vessels. The way we're looking at them right now to model the flow through is that you have to go some simplifications. So once we go under 1 millimeter vessels, my take at this point it is to cut those vessels and actually have it go into a chamber, like a flow chamber, that actually simulates the distal resistance of the tissue. You model what you can get well, but the distal resistance just at this point start looking into a mathematical model, and the lady behind me, this is what she's doing. Flow sensors, pressure sensors, different chambers, see how actually we can control this and create the distal resistance of the tissue. And again, we're keeping the vessels down to about under 1 millimeter distally. We go, I would say it's down to the third branching. But below the third branching, unless we fix the acquisition, we'll not be able to do too well. So it is a combination of reconstruction with, of the CT data and as well as modeling.
Okay, so what I'd done is I took out the vessel where I thought it was too distorted to use, and you can see I cut it off. So I have an open contour here. You can see the inside of what the solid would be. So one feature I really like, it's called Inspector. It will automatically analyze my model and see if there's any discontinuities and try to fix them for me. So here you can see there's a piece that I missed, I didn't delete, it's just hanging off in space, and then this complete open contour. And I can try auto repairing it. And you can see it got rid of that particle that was here, and it closed this contour for me. So then I can go in, I can continue sculpting this vessel however I want, and you can change the strength of your tool. So more or less, you can change the size if you want to do a big portion of your vessel or a small, and how deep it will perform. And you can see I just made a little particulate over there. Oh, nope, it's still attached. I'm going to delete that. And I could go on doing this to make this super small and make sure all the vessels look really good. So I would spend probably 20 minutes to a couple of hours, depending on how good my segmentation was. And once I know that the contours are complete, I'll do that inspect, make sure it's all good. And now I want to make it solid. So what we do is we go into make solid, and it's going to take my anatomy and it's going to extrude it in a smart way so there's no overlapping pieces. And you can adjust how many mesh particles you want, how thick you want it to be. So I'm going to make it 2 millimeters because we find that works really well with the printer. It's robust enough to clean and hold pressure in.
So it puts that on the wall.
Mm-hmm. So it's going to go from my structure and use that as the inner lumen and then go outwards so that you've maintained that inner lumen blood pool. And then I'm going to accept that. And you can see now I have 2 parts here. This is the solid that I just extruded. There, and if I look at the other one, you can see an inner lumen. So if I look at them both together, you see how the middle is the pink, so that was our original, and then the blue is its offset 2. So now they're 2 separate objects. So I want to combine them into one so that I have an internal lumen. So what I'll do is on my internal lumen, I'll flip the direction that it's pointing. So I flip the normals inwards, so that will be a new surface. Because I want an inner lumen surface and I want an outer lumen. So you can make material printed between the 2. And if I add them together in a combined function, and I accept it, now to prove to you that it's hollow inside, I can use some plane cut tools. And now when I go over here, you can see, now you can see down through. And maybe I want to cut one of my coronary arteries, so you can see that too. I'll flip it that way. Now you can see it's hollowed there. And you can change your different shaders, so you can see the translucent view, so you can see the inside. One feature that I didn't show you that may be helpful is add tube. So I just showed you just to make this solid. But what we really want to do is add it to a base so that it can sit anatomical. So maybe I pulled in the spine with me or some other landmark that I know what's supine. So I can go in with some of the mesh mixer tools, just quick like you would in SolidWorks, pull in a square. And when I find it, I can pull it towards me. I can shrink down sizes in whatever direction I want, put it under my model. This is hard when you're doing this on a projector. I'm so used to my chair. And then you can create, I'm not even going to attempt this anymore. You can add base structures to come up to your model, and then use add tube to continue out those coronary arteries. So maybe 3 coronary arteries into 1 outlet tube so that it's more controllable in the lab setting. Then we'll do a final inspect, make sure all the contours are closed, and then send it to Object Studio.
Can you annotate it if you want to?
Not in.
What do you mean by annotate?
So you've got basically an unidentifiable structure because of the file type. And so if you had 40 of those, how do you know that that is 40 and not 39?
Uh-huh.
Excellent question. Yes, you can. I'm going to show Mesh Mix.
You do it.
Here. So you can either do this in Mesh Mixer. There's all sorts of different primitives they have it, but just drag on one and, scale and
But it will print this one.
it'll print it. Yeah, it'll put it wherever you want it. You can separate it, make it out of a different material, scale it, rotate it.
But how big does it need to be to see it? Because if you print them at like 2 millimeters, you can't see the annotation.
Oh yeah, you can, no. It's,
We print it
so
really tiny.
We print ours like 0.5 millimeter.
Really?
Yeah.
Because my 1 millimeter, 2 millimeter, I can't see them.
It might help to change the color.
Okay.
What printer are you using?
I have no idea.
Okay.
Stratasys. That's the correct answer.
We had the engineering school print some models out for us as well, and they have the Stratasys printer down there, and they said one of the difficulties they had was like on a full art model is, I was asking them about, putting a stent through, like posterior circumflex or LED, and they said it's not to that point yet. It is if you do anatomical structures, just as you did there, the vascularization of it, but not on the actual heart model. They said they can't print them out big enough that the lumens just aren't there. So is that something that they were doing wrong, or is that something, is that a technology that is or isn't there? Actual heart model off the CT or off the...
Was it shredded size?
That I would not know. Again, this is just, I asked the engineering school who had the model. I mean, it's great for anatomical models. They print out some fibrotic uterus force, different livers. I mean, we already know that function, printing out vessels, doing anastomosis for our residents and fellows. But the actual heart itself, based off of the CT and the actual blockages in the say posterior circumflex blockage, they said they can't replicate that yet. So is that just a user error, or is that something that can be replicated at this point?
We are also into the business of making software for brain perfusion studies. We have built phantoms with 150 micron channels, 50 by 50, that simulates a tissue of the brain. So it can be done. It depends on the orientation, where the heads go when it prints, the orientation of the object, and how you select. You should go for, when you go for resolution, you should use the strongest support material that you got. Once you print the vessel, it will come up with its inherent roughness on the inside. So you clean the material inside, then you have to use a material, maybe like a sodium hydroxide solution, pass it through, you smooth it out, and then sometimes if you want to smooth it out to make it to the point that it replicates the vessel surface energy, it's the same slip, the way it slips through a vessel, a catheter, let's say, you will have to use some coating on that.
Yeah, so David, we're going to go into the training lab after this, and in there we have a coronary model that we took out the aortic root and isolated the coronary arteries just like this, and we used it with engineers and clinical staff to train them how to gain access with your Judkins left or Judkins right catheter, go out with your microcatheter, actually do a balloon angioplasty, and then put in a stent. We just find that the models over time, if you have a stent putting so much radial force like the coronaries, the model just won't uphold it for very long. Eventually the strain will just give. But we do use fluoro and contrast and simulate that procedure lifetime to do angioplasty. So I'll definitely get on that model with you. Yeah. Any other questions?